Alright, welcome back to the recursion slides. So we're going to have some fun, finish up these slides today. Let's go back to where we ended. We were working on this Fibonacci function, okay? We noticed that it was recursive, and I promised to tell you why this implementation sucks. So here's the code that we wrote last time for factorial, or sorry, not fact. I wanted to copy, not fact, but fib. How dare I? So let's get rid of fact from this folder. Okay, so I've copied fib from last time, and here's the code. We calculated fib of 7, that all worked. Let me try to do fib of 200. It's not too bad, it's only the 200th term in the sequence, right? I'll just wait here. Maybe it'll finish soon. And unfortunately, it will not finish ever. I mean, eventually it might. But the amount of time you will have to wait for fib of 200 for this implementation to finish is actually longer than the universe has existed. So we might be out of luck with that. So I'm going to close that, comment that out. This would take forever. That's no fun, but it's true. Why? Why in the world does that take so long when the other ones will probably work just fine, the other ones that we wrote last lecture? And the issue is, there's a problem with repetition. So when we say fact of 5, or sorry, not fact, fib, when you say fib of 5, it needs to go and compute, all right, what's fib of 4? I'll add that to fib of 3. So it needs to go off and compute fib of 4 first, and then fib of 3 later, after it's done with fib of 4. Okay? So it's got to branch off like this, like the roots of a tree. And fib of 4, of course, is going to call fib of 3, and fib of 2. That's n minus 1, n minus 2. And fib of 3 is, of course, going to call fib of 1 and fib of 2. I should put this backwards because I was following this order, wasn't I? Fib of 2 and fib of 1. It's going to add them together. Fib of 3 is going to call fib of 2 and fib of 1. And fib of 2 is going to call fib of 1 and fib of 0. Fib of 2 is going to call fib of 1 and fib of 0. And fib of 1 is a base case. Okay, so look how, fib of 2 over here is going to call fib of 1 and fib of 0. Now we're done. So here are all our base cases, and we have to recompute those every time. You see that? Also, when we're calculating fib of 4, we have to calculate fib of 2 twice. Oh no. And over here, when we're calculating fib of 3, we have to calculate fib of 2 another time. So you see how this is all getting duplicated? Like all this is getting duplicated right here, it's getting duplicated right here, and all of fib of 3, like calculate fib of 3, that's being calculated over here another time. It's being doubled. It just keeps on being doubled the amount of work you need to do for each larger call to fib. And this doubling is where things go horribly, horribly wrong. You double the amount of work with each new number. It is double as hard to compute. Let's write a better letter. That's horrible. And so 200, it's just not happening, okay? So there is a way to solve this repetition, but that is the topic of a class that is not this one, all right? So I just wanted to point out the problem, but it was very easy for us to think about this solution. Like, this is one of those cases where it's very easy to come up with a recursive algorithm for this sequence. You have to think a bit harder, or expend a little bit more brain power to come up with how to compute this with a loop, with like a for loop or something. Okay, so that is Fibonacci. That is my rant about it. Now let's do just some other more simpler examples that involve printing to try and highlight like how recursion really works and how to think about a problem and break it down and solve it recursively. Okay, so we're going to make this function void print from 1 to and then some number n. So say you wanted to print like from 1 to 3, you would call print from 1 to and then 3, and it would go and it would print, well, 1, 2, 3, right? So we need to find a smaller problem in this one. Okay, this is how we're breaking it down. I'm saying that this has a recursive solution, print from 1 to 3. Can you find a smaller print from 1 to n problem inside of this one? I think you might be able to. And let me just extend this just to make it more fun. Let's pretend we were calling print from 1 to 5, and it would print 1, 2, 3, 4, 5, right? That's what we would like. Can you find me a smaller print from 1 to something problem inside of this print from 1 to 5 problem? And I think you can. I think you're getting the hang of it. Here's one. Well, technically here's one, and here's one as well. They have to start at 1, but here's the next smaller one. Oh man, that screams recursive solution, doesn't it? So that's the recursive case. For the recursive case of print from 1 to n, it's, well, just recursively print from 1 to n minus 1, and you get to assume that this works. You don't have to think at all anymore. It's like, okay, this is going to work. It's going to print from 1 to n minus 1. As long as I build up the answer correctly, it's going to do the right thing. Okay? So after this is done, after this line is finished, what do you need to do to complete this output? The one thing that the recursive case didn't do was print the 5. Okay, so you got to print your n. That's the last thing. All right, and that will be a correct solution. Okay, and then the base case is when do you not have any work to do, or when is it very easy to do something? Like you're going to print from 1 to 5. You're going to recursively print from 1 to 4, recursively print from 1 to 3, recursively print from 1 to 2, recursively print from 1 to 1. You're still doing work. What about this one? Recursively print from 1 to 0. So when you call it with 0, that doesn't make sense, right? There are no numbers between 1 and 0 in that order. So that can be a base case. When you get down to n equals 0, because you're going to keep on whittling down your n with your recursive calls, when you get down to 0, that's the case where you can just print nothing. Okay? And that is a valid example. So let me code this up for you again, and then we'll talk about it some more. Okay? So this is how I want you to think about this when you're solving it. So print stuff. I don't know. Print stuff.cpp. Why not? So print from 1 to, which is the one that I want to explain? 5. Cool. Print from 1 to 5. So it's void print from 1 to, it takes a number n. It's going to print from 1 to that number. It's like, okay, 1, new line, 2, new line, all that stuff. So the base case is if n is 0, do nothing, and in a void function that gives nothing back, if you want to do nothing, you can just say return. Okay, there's nothing to return because it's a void function, but you can return to stop the function and not continue. Okay, else, this is the recursive case. Print from 1 to n minus 1 recursively. You get to assume that this works. Just remember, you get to assume this does the right thing. I cannot stress that enough. All right? You're going to call this function. It's like, okay, I'm going to solve the smaller problem. And because of the magic of recursion, you get to assume that this is going to print correctly from 1 to n minus 1. Because if we build up the solution correctly, it will. It really will. So the last thing that we need to do in the recursive case is, well, we just printed from 1 to n minus 1. If it was 5, we just printed from 1 to 4. Now we have to print our 5, print our n, to solve the biggest problem. And so this is going to work. Let me show you. Oops. 1, 2, 3, 4, 5. And the weird thing is these are all cout lines, right? These are all lines that call cout. There is only one cout in this program. So this line 13 is getting executed with a bunch of different n values in a different order, okay? Isn't that crazy? It's that one line that's doing all this work. That's essentially like the body of your loop, kind of. Okay? This is just getting the work done in the right order, and this is actually doing the printing. Isn't that weird to think about? So let me show you why this is working, and I'm going to abbreviate print as P. So let's do the stack diagram. Okay? So main calls print from 1 to 5, so calls P of 5. And now we're going to do this. So 5 is not 0, so we're going to recursively print from 1 to n minus 1, so that's P of 4, and then we'll worry about printing our 5. Okay? And this is why you get to assume that this is going to work. It's going to do P of 4, okay? And then it'll print its 5 after this is done. Okay, we haven't printed anything yet. So P of 4 is going to come here. Yeah, it's not 0. So it'll print from 1 to 3 first before it prints its 4. Okay, P of 3, which will print from 1 to 2 first before it prints its 3, which will print from 1 to 1 first before it prints its 2, which will print from 1 to 0 first before it prints its 1. And this one is where you do nothing. All right, so that's your base case. This is like your terminal screen output. This is the base case. It does nothing. Returns. Back to who called it. And now P of 1 was waiting for P of 0 to finish. It just did. And it can print its, this is P of 1, remember, n is 1. It'll print its n. It'll print 1 out. That was the first thing. Okay, all these guys are waiting to finish. P of 1 just printed the first number. Okay? And then it's done. Now we're back in P of 2, who was waiting on P of n minus 1. N was 2, so it finished printing from 1 to 1, and now it can print its 2. And it's done. P of 3 was waiting on P of 2 to print from 1 to 2. It can print its 3. It can print its 4. It can print its 5. It's waiting on P of 4 to print from 1 to 4. Now all P of 5 has to do is print its n. Crazy. And then it's done. And now we're back in main, having printed from 1 to 5 in that order correctly. All right. That's not too bad, I hope. So this is the hardest part, coming up with these recursive cases. Okay? So you need to figure out what goes on here. How can I use the smaller answer? Assume it does the right thing. How can I use it to build up the final answer? Okay, so this print n was very important. Okay, let's do print from 1 to n in reverse order. Okay? So print from something to 1. Okay? I don't know what to call it. Could be like void print to 1 or something, all the way down from, I don't know, let's call it print reverse. Why not? From n to 1. Okay, we'll call it print reverse. And so print reverse of 5, P of 5, we want it to print this. And this is how we come up with the recursive case. It's going to print 5, 4, 3, 2, 1. So can you find here a smaller problem? Do you see the answer to a smaller print in reverse from some number to 1? Do you see it? And I think you do. It's this one right here. Print from 4 to 1. Technically, these are also smaller subproblems, but we want the biggest, smaller subproblem. Yeah? So that's P of 4 right there. Crazy. So that is our recursive case. Okay? So in our recursive case, we have some n. We want to print from n to 1. Well, just eventually we're going to recursively print from n minus 1 to 1. That will print from 4 to 1. So that'll do this, 4, 3, 2, 1. And now we have to worry about solving the bigger problem, which is printing from 5 to 1. So when do we print our 5? Do we do it here? No. We do it first now. See that? The recursive call happens after the printing, where here, the recursive call happened before the printing. That was the actual only difference. If you swapped these, it would have done it in reverse, just as we just discovered, okay? That's weird to think about, I know. But this is why it's very important to think about this recursive call doing the right thing and solving it from there. Okay? So the base case is the same. Again, print from 0 to 1 in reverse, do nothing again. Okay? The only difference between this version, this function, and this function is the order in which we make the recursive call in the recursive case. Okay? The only difference. That is insane. And let me show you this. The only difference is, besides the name of the function, print reverse. Yeah, that's all. That's the only difference. And I encourage you to draw the stack diagram for this to understand even better why it's doing this and why you get to assume, like, okay, I get to assume that this is going to print correctly from n-1 to 1. I need to figure out where to put my n to solve the bigger problem. Okay, that was the one difference between this function and this function, where we're putting our n. And that caused it to go in reverse, which is weird, but fun. Okay, so that is that. And now I have just a few more examples, that's all. Okay, so let's do something that's very easy to do with a loop. Let's do it recursively. All right, let's print the characters of a string in order. So like, if the string s was blah, you would print b, then l, then a, then h. Okay? So, again, you can think about it in a base case and a recursive case. Let's do the base case first this time. Okay? So, we need to answer the question of when do we not have a smaller string to print, right? We need to find a smaller string to print and print out all the characters of it. When do we not have anything we need to print? Okay. When can we just stop? What is the smallest problem? Okay. And the answer is the empty string. So if we're tasked with printing all the characters in an empty string, there's nothing to do. That is the base case. Okay. Now the recursive case is the fun one again. You have to find a smaller string in this one maybe, to recursively print its characters out. Okay? So, you can break this down in a couple ways. You need to find a smaller string to print out the characters of an order. You can find this one, that's fine. Or you can find this one. That's another smaller string. Okay? That would also work. So like everybody but the last one, or alternatively, everybody but the first one. See how those are two different candidates for smaller strings? Let's go with the one on top, okay? And so this will be the way we do it. We're going to break down our string this way, into the first character and everybody else. So here's our smaller string, and so if we make a recursive call on this smaller string to print out all its characters, it'll print this for us. And now our job is to print all the characters in the original string. So after, instead of the recursive call, what else needs to happen? We need to print our b. And the b needs to happen before the recursive call. Do you see that? The order is very important, otherwise it would have been reversed again. You want to print your first character first, and then recursively print the rest of the characters. Okay? That's the smaller string, you're printing it recursively. And because there's different ways to break down this string, there are multiple correct recursive cases. This is just one of them. Okay? Let's do it. And then we'll do it in reverse just to show the difference. Okay? So this is still print stuff. Why not? So I'm going to do something like, I don't know. Did I give it a name? No. Print chars. Print chars of some string, blah. So let's include string. There we go. And so again, base case, recursive case. If s is empty, just return, nothing to print. Else, otherwise, we want to print the first character. That needs to happen. sorry, s.at 0 is the cooler C++ way of doing that. And then we need to recursively print the smaller string, okay? And the smaller string is every character but the first, all right? So how do we do that? We need to find out how to like erase the first character out of S. And one way to do it is with s.erase. Say s.erase, and it erases at a certain position a number of characters, okay? So erase starting at index 0, 1 character, and this will change, I believe it should change S itself. If it doesn't, we could assign this equal to something. So S should now be smaller, and we can recursively print those smaller characters. Print the characters in the smaller string. So S has been changed now, I think. So let's see if that's going to work. Yeah. So S is now smaller. So cut off the first character of S to make S smaller. That's now, even though I'm saying print chars of the same thing, same variable, I've changed the variable. Okay, that's the idea. Okay, so that's print chars. Hopefully you can see this. I do encourage you to draw the stack diagram. This is very similar to printing in order or in reverse order. We had to figure out where was the smaller thing, and in which order do we make the recursive call before we print something else. Okay, in this case, the B needed to be printed first, our first character needed to be printed first, and then we made the recursive call to print the smaller string. Print the characters of the string in reverse does the opposite. So, again, here is our, how do I want to do this? Here is our string. That's technically not what we want. Oops. Here's our string. Let's get rid of this one. What we would like to print now is not blah, but halab. Yeah? Or, sorry, halb. There we go. So we want to print them in reverse order. And this is still the smaller string, so I need to print this in reverse order with the recursive call, and that will print hull, right? That's the recursive call right here, printing hull. And then I need to make the whole thing work, solve the biggest problem. I need to worry about the B. Where does the B need to come? After the recursive call prints the others. See that? So the order is different now. Base case is the same, the order is again different. That is all it takes to make this function do it in reverse. So, let's see here. I should save the first character maybe, because I'm about to delete it. And then, boop. Recursively print the smaller string in reverse, because you get to just assume this recursive call is going to work. And do the right thing. You can assume that, because it's a smaller thing. And then you just need to worry about printing your first character, okay? Okay. Okay. And we needed to save that because otherwise it would have gotten erased. All right. So let's call that. Oh no. Yeah, Halb. We did it. So that is all it takes to ruin your day, because the order is very important. So always think about the recursive call, what it gives you. It's going to correctly solve it. You get to assume that, as long as you build up the answer correctly. Okay. Another example. Let us take a C string this time, not a C++ string, and capitalize it. All right? So we're going to capitalize a C string. So we're going to turn in a C string that looks like this, like S1 or something. We're going to turn it into, from this, like if it were blah. Remember, it has that null terminator character at the very end. We're going to turn that into, somehow, a new version of S1. We're gonna like update it in place, I think. How about this? Still S1. We're just gonna have changed it into this. Capital B. Capital L. Okay? Capital A. Capital H. And then keep the null terminator character. Okay? So this is what we would like to do. And again, we can split up the string into the first character and then the rest of the characters. And that'll make us a smaller string on which to do recursion. Okay, because we always need something smaller, and this is a nice smaller thing, a smaller string to give. Okay, so in the recursive case, what we can do is this. When we make the recursive call, we can assume that this is going to correctly become, it's going to turn this into BLAH, like that, with all these rest of the characters capitalized. It's our job to solve the bigger problem for the biggest string. We need to then go and capitalize the first letter. Okay, that's what we need to do. This is what the recursive call gives us. Recursion gives us this, we can assume, and then we can just fix it by capitalizing the first character. Okay, that's what we need to do. That is what we want. And in the base case, the easiest thing to do is think about, like, what's a string that we don't have to capitalize anymore? Like, we can immediately return, there's nothing to do. And that is the empty string. Okay, so again, the base case is the empty string, because if you just have like \0 in your string to capitalize, well, you don't have to change a thing, it's still the empty string. Okay, so yeah, this is how it works. This is the recursive case and the base case. Let's do this. Let's make this happen. So we're going to come back to this in just a second. We need that, but let's get to needing it. All right, so let's do it down here, I guess. Capitalize. It's going to take a C string, okay? That's a char star, or a char array, whichever one you want to think about. Char star str, or S is fine, I guess. And it's just a void function. It's going to edit the string in place, okay? Capitalizes the string recursively. The C string S recursively. And so, in the recursive case or the base case, we need to figure out where we are, right? We're in the base case when our string is empty. How do we know when our string is empty? Well, that's when the string's first index holds the null terminator character. That's when we know we're empty, okay? So if S of 0 is equal to the null terminator character, then we're in the empty string. And you can just return. Okay, so that's the base case. Else, recursive case. Then we need to recursively capitalize the smaller string and also capitalize the start of the string, so the very first character. So that is S of 0 equals 2 upper, I think, 2 upper of S of 0. Yeah. And for this, we need CC type. So there we go. And that is good to go. And now we need to recursively capitalize the smaller string. So we need to call capitalize on the smaller string. How do we do that? How do we find the smaller string to capitalize? And here's the answer. So remember that a C string, if it was this, like A, B, C, null terminator, and it was called S2, really, S2 looked like this. It was a pointer to the start of the string. Okay? So the smaller string is over here. We just need a pointer to it. Okay? And we can use our original string. We can just add 1 to that, to whatever like address this is. If this was address 100, this is address 101, and so this holds 100. We can just say S2 plus 1. That's 101. And that gives us a string starting here which from C++'s point of view is a string of a smaller length, okay? Because that's all a char star is, that's all a C string is, it's a pointer to the first thing. So this is how you give it the smaller string, s+1, okay? s+1 is the address of the smaller string. Okay, that is the idea. Capitalize s+1. It looks weird, I know, but you're just advancing pointers, and it's going to be capitalized. All right, so let's make a C string. Let's be like char s, I don't know, s1 equals blah, and we'll do capitalize of s1, and then we can print out s1. Because it's a C string, C++ knows how to print it, even though it's like declared as an array. Aha! All caps. We did it. Okay? So slowly but surely, with enough examples, I hope this idea of recursion, doing the same thing on a smaller problem, and assuming that it's going to work as long as you put up the final answer correctly, that will do it. That will solve the whole problem. Okay? So this is just a weird little example where we did some pointer arithmetic, which is helpful to know how to do. Okay? A nice little example there. And then my most in-depth example is this one. Let's scramble all the characters of a word. All right, so let's find all the permutations of all the characters of a word and give back a vector of all of them. So for example, we wanted to find all the permutations, let's call it like perms or something, of the string A, B, C. And so we want to give back a vector of all the different ways to permute the letters A, B, C. So of course A, B, C is one of them. Then there is A, C, B. Then B could come first, B, A, C, B, C, A. C could come first, C, A, B, C, B, A. And I think it's going to be 3 times 2 times 1. That is 6 total possible permutations. Okay? We want to make a function that gives back all of them. Crazy, huh? So that's what we want to do. We need to somehow find smaller word scrambling problems inside of this one, which is weird, I know. We'll find them, and then we'll think about base cases and recursive cases. Okay, so let's find the smaller versions of the scrambling problem first. Okay, so here's the way I want you to break this down. This is the secret. So the idea is we're working on this string, trying to permute all the letters. What we have to do is first pick the first character in the scrambled string. It's going to be either A, B, or C in this case. We've got to pick one. And then if it's A, we need to then go and scramble B and C. If it was B, we need to go and scramble A and B. If it was C, we need to go scramble... Oh, sorry. This one was A and C. This is scramble A and B. And once you've done that, like scrambling B and C, that's, okay, it's BC or CB. Then you plop the A at front of both of these, of the BC and the CB. Okay? And those are your permutations with A at the front. And similarly, we can find all the permutations with B at the front, all the permutations with C at the front, by scrambling the other characters. Okay? That is the trick. Okay, so now we can think about base cases and recursive cases. The base case of this is when we have nothing to scramble. Okay? There's no need to scramble. We can just give back an empty vector, a vector containing the empty string. When there's nothing to scramble, like, okay, give me all the ways to permute the characters in the empty string. Well, there are none. There's just one, right? There's just one empty string. There's nothing else. Okay? That is the way we want to do that. Okay? So that's the base case. And the recursive case is kind of what I just explained. We pick a starting character, and we have to try them all, and then recursively scramble the remaining characters. We get to assume that it's going to do the right thing. It's going to find the BC and the CB, or the AC and the CA, all that stuff. And we build up the result vector by taking the starting character, like this is giving back the vector BC and CB when we scramble B and C. We need to go through this and put A at the start, okay, to make ABC and ACB. Okay, do you follow that? It's a weird one, I know, but that is going to be the solution, and this is a fun one to study and to think about. So here we go. This is going to be, let's do a different file for this one. This is getting a bit big here. So let's call it scramble.cpp. So let's, we're going to scramble all the letters in ABC is probably good enough for now. We can try bigger ones later. So we need to get back all the permutations after scrambling ABC. Okay, so we need string and vector. So now we need scramble, and it's going to give back a vector of all the scrambled strings, okay? All the permutations. And this could just as well be constant and a reference, so why not? And that is what we want, okay? If we can define this, it will work. So here we go. Are you ready? So in the base case, when there's nothing to scramble, give back the empty string. We want to give back a vector containing the empty string. All right, so like vector string result equals just a vector containing the empty string. That's the one way to permute all the characters. There are none. Else, this is the recursive case. What we do is we pick a starting character, having tried them all though, so we have to iterate through everybody for for every character in the string S. We have to try every character. We let them all have a chance being the starting character. And then we recursively scramble the remaining characters. Okay? So actually it might be easier to iterate in the normal way. Because here's what we could do. We could say, all right, the current character at the front is S at I, and then we need to get a string of the remaining characters so that we can use recursion. So we need to make a string of every character other than the ith character. So one way to do that is string, smaller string, it equals S, but we're going to erase index I, because that's the one we're currently using for the starting character. Yeah, see that? So the smaller string now is going to contain every character but the ith character. And then we also saved the ith character. That'll be the starting character. So it's either A, B, or C in this case. If it's A, we just made the string BC, for example. If it was B, we just made the string every character but B, we made the string AC. Okay, and we're going to go scramble that. So that's the idea. We're going to get the remaining characters to scramble, and we're going to scramble them recursively. We get to assume that this is going to work, which is the magical thing. We're going to get back a vector of strings, permutations of the smaller string, or we'll just call it perms, equals scramble the smaller string. And this will give us back all the permutations of the smaller string. So like if it was B and C, it'll give us back B, C, and CB. And then our final answer needs to include A at the front. Okay, we need to put A at the front of all of these strings that we got back. Oops, let's go there. So put starting char at the front of every string in perms. We're going to have to iterate for string S, and let's call it something other than S, for every, I don't know, string perm in perms. And you can use the normal recursion or the fancy for loop with the colon, the for in loop for each loop. And I need references because I need to change this thing. You can say perm, whatever this current permutation is, it's whatever it was, but at the front we're going to put the starting character. See that? And now perms contains, for each example, we have, if it were A, now it has ABC and ACB. If it were B, now it has scrambled A and B, or A and C to be AC, and CA. And so it'll give back BAC and BCA, because it's going to put the B at the front of all of these strings. Okay? This is an extended example that I wouldn't dream of asking you about on a test, but it's a fun one that shows you the power of recursion. It's very hard to think about this problem any way other than recursively. Okay? So now, the answer, I need to, like, all of these are part of the final answer. I need to put them all in one place. Okay? Add these to the final answer. Add perms to the final answer now. So I need to make some kind of res vector again. It can start out empty, but we're going to add to it. So for example here, we can add to it. Okay, so again, for string perm in perms, we're going to push it back to res. Okay, add everybody to the final answer. And then at the very end of all this is the else case still. Once we've finished adding to res, return res that has all our permutations that we were all building up in all of these cases. We picked a starting character, we recursively scrambled the rest of the characters, putting the starting character at the front of all of those permutations, and finally adding to our result set. So I'm pretty sure we have done everything. I might have made a silly mistake somewhere, and we will see that soon enough, but that is how you scramble all the things. So now you can say for, I don't know, string S in permutations, you can see out every permutation now. Oh no, it's not print stuff. Now it's scramble. And oh man, do we get all 6. And if I change this to D as well, we double the amount of permutations, right? Or not double, but like multiply by a larger number. Because it goes from 6 to 4 more, right? Times 4, 24. So all the A's coming first, all the B's coming first, and then you scramble the rest of the characters, the A, the C, and the D, in all the different ways, putting B at the front. Okay? This is very hard to do without recursion. Okay? That is scramble. It's a fun little example, and I think you're going to do something similar in your book, but slightly different. Okay? Where you're going to not use a vector, maybe. But this should be very helpful for that example there. Okay. So the final thing that I want to talk about is just a very classic example that I want you to have seen before. I'm not going to test you on this. Don't worry about like understanding it. I'm just going to go over it quickly so that you understand like how this might be recursive. But there's this problem called the Tower of Hanoi, right? And you might have seen it before. There's like a bunch of pegs on, or there's a bunch of disks on 3 different pegs, and the name of the game is to take all of these and put them on this peg over here, all the disks onto this peg. And the rule is that you can only stack smaller disks on top of larger disks, okay? So you can't have it backwards like this. That's a hard rule to follow, okay? So that makes it difficult. And so you can move this one here, but you can't put the second one on top of it because now it's bigger, okay? So that's the game you have to play, and this can actually be solved recursively to move all of these over to here, okay? There's a concept of like the source peg, the like intermediate peg, and the destination peg, okay? And so the base case is when you want to like move the smallest disk. You can put it wherever you want because it's the smallest. It can go anywhere. And then the recursive case is to move a stack of disks. So everybody but the last one, for example. You can recursively move those over to like the intermediate peg, and you can assume that the recursion is going to correctly follow the rules and move this smaller stack down to here. And the idea is then you have this last peg sitting out at the very bottom by itself, which you can then finally put right here at the destination. Okay? And then now this is all empty. And then you move this entire stack recursively up here. Okay? Because now the biggest peg is here, and you can recursively move them all down to here from this place, using this now as the intermediate peg because it's empty. So don't worry if you didn't follow any of that. I think your book has a fun example, or the internet does at least. If you're interested, I'd be happy to talk to you about it more. But this is like the idea in words, and it's a fun little graphical example of recursion if you'd like to look into it. Okay, so that's the Tower of Hanoi. It's a fun one. And yeah, that is all. You are now masters of recursion. So this was a hard set of slides. It's a hard chapter in the book. So pat yourself on the back if you understood anything at all. It does take a while to sink in, so don't worry. Please come yell at me with any questions that you have. So yeah, some nice exercises that could help you is to realize that anything you can do with a loop, you can do with recursion. So take some examples using loops, while loops and for loops, back when I first taught you those, and maybe try and convert those examples to be recursive functions that either calculate the result I was showing you that we could calculate, or like performing the operation that the loop was performing. Okay? Maybe it had to print a bunch of stuff. That's the idea. So the more things you can convert from loops to recursion, the better you're going to get at it. Okay? And I'd be happy to help you with anything. So please do not hesitate to yell at me about that. And I think that is all I have for you. So that is the end of these slides, and I will see you later.